Hey, welcome back. This is Lesson 10 and our third unit of AP Calculus. This unit has been all about the rules of differentiation. These rules of the game that you have to learn and remember in order to apply and use the derivative. Today, we're going to finish this unit up with one last lesson, and in this lesson, we're going to tackle the inverse trig functions. They're extremely important, and they became a bridge between a lot of different parts of mathematics. So it's really important that we understand them. But the formulas, they are a little bit clunky to remember, and I apologize for that, but I didn't do it. It was calculus that did it. But they're super important, so let's give it our best shot. Each trigonometric function has an inverse function associated with it, as long as we provide some restrictions. For example, the inverse of sine of x, which can be written as sine of x, sine inverse, like this, or as arcsine, has a restriction that restricts its range from negative pi over 2 to positive pi over 2. If we don't restrict its range, then it wouldn't be a function. So these restrictions are best thought of as regions of or quadrants of the unit circle. So we know that the arc functions, the inverse trig functions, give an angle associated with a certain ratio. So for example, sine of x gives a trig ratio associated with an angle x. Arcsine of x gives an angle associated with the ratio x. And we're going to limit that angle to just certain quadrants. For all of our kind of what I think of as cosine-based inverse functions, we're going to be limiting to the top two quadrants, quadrant 1 and 2. So arccosine, we're going to limit our range from 0 to pi. And that is because the entirety of the range of cosine is covered in this interval here. So from 0 to pi. And so therefore, it should not surprise us that the limits on arcsecant and arccotangent are related, because they are all kind of cosine related. Cotangent has cosine in the numerator. Now, in most pre-calculus classes, you just learn arccosine. But we should probably go ahead and talk about arcsecant, and you won't see arccotangent too often. But arcsecant is one you probably want to know. And it has the same limitations as arccosine. But notice that we don't have pi over 2. That one's not included because you never get pi over 2 as a value from arcsecant. All right. Arcsine, on the other hand, and arctangent, well, they're limited to quadrants 4 and quadrant 1. Unlike cosine, which arccosine, which can give obtuse angles bigger than 90 degrees over here. Arcsine and arctangent only give acute angles, but some of them are positive and some of them are negative. So it goes from negative pi over 2 to pi over 2. And it's very important you keep those ranges in mind, okay? Let's take a look. All right, we're going to evaluate each, but we're only going to use calculator if necessary. The arcsine of negative 1/2. Well, we need to think about what angle measure has negative 1/2 for its trig ratio. Well, you should recognize that it's going to have to be in quadrant 4, because arcsine is limited to quadrant 4 or quadrant 1. And since sine is negative down here, it's got to be down there. And hopefully remember that it's the sine of pi over 6 angles that are 1/2. So this is negative pi over 6. All right, cosine inverse, just another way of saying arccosine of negative root 2 over 2. Well, arccosine is limited to quadrants 1 and 2, so that's going to be over here where we have negative root 2 over 2 for the cosine values. And so that is going to be a pi over 4 angle, and it'll be 3 pi over 4, because the angles over here have a numerator of pi, one less than the denominator. And finally, arctangent of 0.3, negative 0.3. Well, we'd have to use a calculator for that. I'll just pull up Desmos right quick. So arctangent of negative 0.3, and we'll say it's negative 0.291. And you need to be able to find that button on your calculator, whichever one you're using, so make sure you practice that. All right, let's take a look at the relationships when we start having sines and cosines and such of arc functions. So the arccosine of 4/5 is an angle. I don't know what it is because it's not on my unit circle. And we don't need a calculator to evaluate this. Instead, let's draw the angle on our coordinate plane. Arccosine is either in quadrant 1 or 2, and it's positive over here in quadrant 1, so I will draw that. Cosine ratio is adjacent over hypotenuse, so this must be 4, and this must be 5. Well, this is a 3, 4, 5 right triangle, so this must be 3. So arccosine of 4/5 is actually returning this angle of this triangle, this 3, 4, 5 triangle. So we really know that this is asking us just to find the sine of theta, where theta is in this triangle, and sine is opposite over hypotenuse, so it's 3/5. All right, what about sine of arccosine of x? Well, I don't know what quadrant that's going to be in because it's just in x. But it turns out it doesn't matter. So we can just say x and put it right there. Well, if this is x, we know that arccosine returns this theta, and cosine is adjacent over hypotenuse. So x is this bottom length, and 1 is up here. So we have to use Pythagorean theorem, and you square that and subtract that squared. So it's 1 squared minus x squared. So then the sine of this angle must be opposite over hypotenuse, so it's the square root of 1 minus x squared. All right, very good. Let's do the next one. Secant of arctangent of 3x. So the arctangent of 3x, we can draw it in either quadrant 1 or 4. We'll just stick with right here. It makes sense. And arctangent is opposite, is the ratio, the angle from the ratio of opposite over adjacent. So 3x over 1. And that makes this the square root of 1 plus, because we're adding for the hypotenuse, 9x squared. When I square this, I get 9x squared. So secant is hypotenuse over adjacent, so this is simply the square root of 1 plus 9x squared. Okay, so let's take a look at our derivative formulas. The derivative of arcsine of u is u prime over the square root of 1 minus u squared. And arctangent, we saw that earlier that it had a plus in it, right? When we were doing that conversion, and arcsine had a square root. So you can imagine that's kind of where they come from. Well, arctangent u is u prime over 1 plus u squared. The derivative of arcsecant u is u prime over the absolute value of u times the square root of u squared minus 1. Eek. You won't see that one too often, but we're going to learn it, but it's not that common a formula, at least in our AP calculus. Arccosine and arccotangent and arccosecant are exactly the same formulas. They just have a negative. Remember, you're taking a derivative of a co, you have negative in your answer. So I'm going to argue, if you remember that rule about the negative with the co, I'm really only giving you 3 new formulas today. And they're your last 3 trig formulas of the unit. I think we have a couple more next unit, but they're not too bad. All right, so there they are. Now, we'll prove them at the end of the lesson, just because I don't want to take time right now while we're on a roll. So let's go right into practicing to use them. Keep these formulas handy till you memorize them, but you do need to memorize them. Go ahead and pause the video and try your best to do these. Okay, the derivative of arcsine of u is u prime over the square root of 1 minus u squared. So f prime of x is u prime over the square root of 1 minus u squared, which is 4x squared. Remember, that's the formula right there, 1 minus u prime over 1 minus u squared. All right, what about arctangent? Well, the derivative for arctangent is u prime over 1 plus u squared, and it's not it's not in a square root. Remember that? It's not in a square root. All right, lastly, we have arcsecant. And the formula for arcsecant, the derivative of arcsecant u, is u prime. So that's e to the 2x times 2, because the derivative of the e to the 2x is e to the 2x times the chain, over the absolute value of u times the square root of, this time you start with u squared and then minus 1. The square root of u squared, which would be u to the e to the 4x, power to power multiply, minus 1. Now, it turns out I actually don't need the absolute value bars here, and the reason why is that e to the 2x can never be negative, so that's always going to be positive. So in this case, I don't actually need them, but you oftentimes do. I would say you in general, you do. Now, something else happens on this one as well, though, and I know I don't usually tell you to simplify, but something happens here. Because we remove these absolute value bars, those actually get reduced down. So it's kind of interesting, right, that you get 2 over the square root of e to the 4x minus 1. So a lot of simplifying can happen on that one. All right, let's take the derivative of cosine of arcsine of 3x. All right, the derivative of this can be found using our we can definitely use our trig formulas, but there could be another way to do it. Let's start with the trig formula. We need to use the chain rule. The derivative of cosine u is negative sine u prime. So now I got to multiply by the derivative of the inside. Well, the derivative of the inside is the derivative of arcsine u, which is u prime over the square root of 1 minus u squared. Oh, that'd be a 9x squared now, wouldn't it? Now, what is the sine of arcsine of something? Well, those are inverses, so they should cancel out. So this should really be negative 9x over the square root of 1 minus 9x squared. So why did that happen? How could we think of this another way? Well, let's talk about what the cosine of arcsine of 3x is. Well, arcsine of 3x is really the angle that's made by this triangle here in quadrant 1 that has an opposite leg of 3x and a hypotenuse of 1, because it's opposite over hypotenuse, which means the adjacent is 1 minus 9x squared, right? So this f of x is really the cosine of this. So f of x is really the square root of 1 minus 9x squared, which we know is 1 minus 9x squared to the 1/2, which I can take the derivative of, and I would call it, let's see here, 1 minus 9x squared to the negative 1/2 times derivative of the inside, which is a negative 18. Oh, I forgot to bring down the 1/2 in front, which is a negative 18x. Kind of running out of room there. All right, so how does that all simplify? Well, the 1/2 and the 18 make this a negative 9x, right? A half of 18, negative 18. And then this just goes to the bottom, and I can put it back in a radical if you like, because it's to a 1/2 power. And that's exactly what we got. So either way, you get the same answer. Kind of cool, huh? All right, I think I got some more practice for you to do. How about this one? Can you find the equation of the tangent line to f of x equals 1/2 arc cosine x at x equals negative root 2 over 2? Pause the video, take your time, get it right. Okay, so to find the equation of a tangent line, I need the slope and the point of tangency. So let's find the slope at the point of tangency. For that, we need the derivative. That's f prime of x is equal to 1/2. Now the derivative of arc cosine, we didn't have any arcs earlier that were like that, did we? Huh, that's weird. Okay, so this is our first arc cosine. Let's be careful. That's the same formula as arc sine. It just has a negative. So I'll put the negative right there. The derivative of arc cosine is u prime, so 1 over the square root of 1 minus u squared, in this case x squared. But don't forget about the negative. I just put it out in front. I don't want you to think I forgot it. So this is a negative 1 over 2 times the square root of 1 minus x squared. Now let's evaluate that at negative the square root of 2 over 2. Well, that would be negative 1 over 2 times the square root of 1 minus root 2 over 2. Now, I really don't like root 2 over 2 that much because you know what it really is? It's really just 1 over the square root of 2. Wouldn't that have been easier if we had just, realized that? But because then you realize that this is just 1/2 when you square it. But you can go ahead and do it if you want. Square that, you get 2. Square that, you get 4. It's still just 1/2. All right. Well, that's a big old ugly thing. If it's a free response question, you don't need to simplify it. But just for funsies, let's go ahead and do it. 1 minus 1/2 is 1/2. So this is the square root of 1/2, which means you have negative 1 over 2. The square root of 1 is 1. And the square root of 2 is the square root of 2. All right, so I've got a square root of 2 on the bottom here. I'm just going to kind of like keep change flip and make it negative the square root of 2 over 2. Well, that's weird, right? Well, that's what happened. All right, so now I need to find the y-coordinate. Well, the y-coordinate is f of the negative square root of 2 over 2. Which is 1/2 arccosine of square root of 2 over 2. That's 1/2 of negative square root of 2 over 2. So that's 3 pi over 4. 3 pi over 4, which is 3 pi over 8. So finally, we can write our equation of our line, which is y minus the y-coordinate equals slope times x minus the x-coordinate, which is makes it a plus root 2 over 2. And that is all for that one. And I think that's it for that lesson. So the only thing left for us to do really is to go over the proof. What I'd like to do is I'd like to prove, let's prove arcsine and arctangent. Now, the others are pretty much related, so I'll let you do it on your own. The arcsecant one is weird because of the absolute value, and it's a little unclear why that has to be there until you really go through a lot of steps. So I'll leave that for you to... There's plenty of resources on the internet if you're interested. But it's, the basic premise is the same. So let's just do the arcsine and arctangent. So we're going to start with the derivative with respect to x of arcsine of x. That's what we're trying to figure out. Well, I'm going to say, let's let f of x equal sine of x. And that means that f inverse of x is equal to the arcsine of x, right? And we know that f inverse prime of x is equal to 1 over f prime of f inverse. Don't forget that order. That order is really important. F prime of f inverse. And we know that's true. That was a simple application of the chain rule. That's an easy little proof. So we're going to use that to help us figure this out. So I know that f inverse prime of x in this case, well, what is f inverse of x? Well, f inverse of x is arcsine. So I have f prime of arcsine of x. Well, what is f prime? Remember, we said f was sine of x, so that means that f prime is cosine of x. Okay, so that means that if I have f prime of arccosine of x, that means I need to put this right here. This arcsine of x needs to go in for x here. So let's do that. 1 over the cosine of arcsine of x. All right, well, now we just need to evaluate that, right? We just need to figure out what is 1 over the cosine of arcsine of x. And we did that earlier, so we're just going to draw a picture. That's the way that works. My first quadrant, I'll just say that x is here. So arcsine is this angle theta. Remember, arcsine gives you an angle. The sine ratio is opposite over hypotenuse, and so this adjacent leg is 1 minus x squared. The cosine of that would be this over that. So it would be 1 over the square root of 1 minus x squared. So that is the derivative of f inverse prime of x, but we said f inverse was arcsine. So that must be the derivative of arcsine of x. And you can simply use the chain rule to get the general version of that. All right, next, let's do arctangent. And it would probably be a pretty good idea for you to pause the video and try and figure it out yourself. We're trying to prove the derivative with respect to x of arctangent of x. And it's going to be exactly what we just did. So give it a try. All right, I'm going to let f of x be tangent of x so that I can have f inverse of x be arctangent of x. All right, so we know that the derivative of an inverse, which we call f inverse prime of x, is equal to 1 over f prime of f inverse of x. So for us, that's 1 over f prime of f inverse here is arctangent, right? Well, what is f prime? Well, if f is tangent of x, then f prime of x is the derivative of tangent, which is secant squared. Remember that arctangent formula didn't have a square root in it. All right, it makes sense, doesn't it? So this is going to be 1 over secant squared of arctangent of x. Well, we can figure that out, right? We can do that. We know that arctangent of x is going to give us an angle theta. Tangent is opposite over adjacent, so it's this angle here. And it makes the hypotenuse the square root of, x squared plus 1 or 1 plus x squared, either way you want to write it, right? So this is 1 over the secant squared of that. Well, the secant of this is cosine flipped over, right? So the cosine of theta would be 1 over root x squared plus 1. So secant is root x squared plus 1 over 1. So this is just, the secant of this is the square root of x squared plus 1. But don't forget, we're squaring that because it's a secant, and then you square it. So this is just 1 over x squared plus 1, which is what we were trying to show. So there you go. Nice little application of the inverse of the derivative and inverse function formula. That's the end of the unit. We do have a couple more derivative rules to learn. They're kind of optional because you can get them on the fly using the technique that we'll use to derive them so quickly and easily that they're not an absolute mess, but they kind of make things a little easier. So we'll talk about that when they come up in the next unit. Our next unit is going to be about what I call advanced derivative techniques. We'll start to look into applying derivatives, but we'll look at some more advanced derivatives first. Then we'll start applying, and then from there we'll have a couple units where we are just working to apply and use this derivative now that we finally know how to do it with great skill. So until then, take care.